Everyone, and welcome to another live video here on Freaky Physics. And well, I'm a bit late today, so I'll just get into the class right now. Right, let's join.
Hello.
Hello and good afternoon, Gita. How's everything today?
It's good. I'm a bit sick. I
Yeah,
think
me
you are
too.
too.
Me too, but yeah, I can still manage. I
One moment.
Go ahead.
Sorry.
No problem. All right, so let me see here. You sent over a lot of problems today.
I
Okay.
thought they would be really quick, but if we don't manage, we can finish another day.
No worries. I think we should be able to get to everything. Well, at least most of these today. All right.
Mhm.
All right. Let me start off by where is that? Okay. Let's just open the board. Then let's start. All right. So let's also share the board here.
Okay.
Okay. All right. So where were we? Okay. So here we are. And excuse me. Where's it? Here. All right. So with this, let's start. Okay. First thing. Let's take a look at the first problem you have here. Oh, okay. This one's pretty easy. Okay, so the first problem here is about a solar panel, right? Um, let's get it into the screen. So there's a solar panel and it transfers energy at 2.4 kilowatt rate to a liquid passing through it. The liquid has a heat capacity of 4,000 joules per kilogram per Kelvin, and the temperature of the liquid increases by 6 kelvin when it flows to the solar panel. Okay, what's the flow rate through the panel? Okay, all right, we have to start here with the idea of that the energy needed to heat up the water would be equal to mc delta t. Yeah.
Yeah.
Okay. However, because of this already tells us that we need to somehow put time into it. So we're gonna have to do divide this by time, so that's gonna be power, right? But also
Yeah.
we need to divide the whole thing here by time. Excuse me. So what we're gonna do here is we're gonna put 2,400 watts here. And that's gonna be equal to specific heat capacity is given. So we are looking for m over t now because c is given as 4,000 and your delta t, your temperature increase, is 6 Kelvin. Yeah.
Yeah.
Okay. So this is, what's the unit here? Joules per kilogram per Kelvin, right? So this Kelvin cancels out, and then this is, let's replace it with joules per second. So the joule here and this joule here cancels out. So from here, it's very easy to get it now that m over t, and that's the thing we need, is going to be equal to 2,400 divided by 4,000 times 6. Since this is no calculator, this should be easy to divide. This gives us the 6 cancels out with this. This becomes 400, right? And we can already see what the answer is. It's going to be 0.1 kilograms per second. So
But sorry.
go ahead.
Um, how could we just ignore the 406? Should we not have to divide it to the other side?
Actually we did. That's what we did. So let's do that again. So what I did here is I basically put it to the other side, and to do that we're gonna divide by 4,000 times 6, right? So divided by 4,000 times 6, and we're doing the same thing here. 4,000 times 6. Okay, so this whole thing cancels out. We're left with m over t is this. And so we get 0.1 kilogram per second.
Huh.
Okay,
Okay. And sorry,
go
I just
ahead.
want to cancel the options. I didn't get it at first, but then I redid it and I did 2,400
Right.
times 400 times x6 times 1
Mm-hmm.
because I was trying to find the first temperature and then
Uh-huh.
I got 0.6 over 6 is 0.1. I don't know
Uh-huh.
if that makes sense.
Okay.
But I did it by finding the last temperature.
Okay. Actually, you don't need to find the temperature, or yeah, the initial and final temperature, because in the formula you just need the difference in the temperature. In this,
Right.
because of the word here, it's increasing. That's already your delta t. Okay.
Huh.
Okay.
Okay.
Right. Got that. All right. Let's go to the next one. Okay. So the next one here is about light of intensity I and wavelength. Okay. Quick question. Sore throat,
I had a fever yesterday.
fever, sore throat, maybe somewhat like a cold.
Yeah.
Yeah, I think that's the virus that's been on the news, but you know, it's I've read about it. It's not really that serious. So
Yeah.
we
Well,
just need to get
yesterday
through it.
felt
Yeah.
hopefully.
Mm-hmm. Image. All right. Um. Okay, where were we? Okay, here we go. So here's the problem. So light of intensity I and wavelength lambda is incident on this. Okay, so if we go here, we need data booklet. We need the formula for what's this? The single slit equation. In other words, this is part of the
It's
HL material, right?
yeah.
Okay. However, we don't really need the equation straight away. We'll do this in terms of the equation first, and then I'll show you a way to kind of intuitively get the answer. Okay.
Hmm.
All right. So first of all, where's the data booklet? Let's take a look at. Yeah, formula is uh, thermodynamics. Here, wave behavior. Uh, wave phenomena. Okay, here.
And lambda.
Yeah, that's the formula
Okay.
here. Correct. So that's n lambda equals d sine theta, right? Wherein
Yeah.
if you draw this properly, this is gonna be your theta here, right?
Hmm.
What's our n in this case? We can usually just assume that n is 1, right? So from here, what we can kind of figure out is lambda is proportional to d, right? So
Yeah.
if you increase, there's something else missing. Okay, there is the width. Okay, if you do the one with the width though, which formula is it gonna be? It's okay. That's for double slit. So from here it's not very obvious what's gonna happen, right? But if you think about this sine theta part here, again intuitively, if you put theta there, that means theta's gonna be here, right? So theta would be equal to, or let's just do sine theta. That no tangent theta would be easier. Okay, so tangent theta would be equal to um opposite. That's gonna be w over d. Okay, so in other words, if you do this further, this becomes lambda is proportional to w, right?
Oh,
Okay,
yeah.
so the answer here is what change will increase the width of the central maximum. There are several ways you can do it. Um, let's take a look. If you wait, okay. All right, so if you increase W, it will... Ah, okay, hold on, hold on. Give me a moment. I just realized the other options are not like that. Okay, hold on. So, okay, so here's the thing. Doing it with the equation is kind of difficult. You really have to do a lot, right? So let's do intuitive sense first. Okay, so going back to the equation going back to the equation first. Think about it this way: when you have a big slit, the light just passes through, right?
Yeah.
Okay, and then when you as in you have a really big hole, right? And then when you get to when you make the hole smaller and smaller and smaller, at least before we see the interference pattern, we see that the amount of light falling into the middle gets smaller and smaller and smaller. It's like it being covered by a shadow, right? So this is what I mean.
Mhm.
So for example, our light source is only this big. It's only that big, right? So
Yeah.
in this case, our maximum is just gonna be that big as well, right? But when you move this down, when you make this smaller, eventually this becomes. So if we do the same thing to a big enough size hole, the light is going to just stop right there. So that's the normal thing we see. So that's what we think first. Before we do the weird physics, we'd go to the everyday physics first, right? You get the
Mhm.
idea? So as you make W bigger, as smaller, you will see that this actually gets, as W decreases, the what's this? The central maximum also decreases, at least to a certain limit, right? Okay. So so that's the first part. So this is gonna be wrong. Double decreasing W will be wrong. Okay. Now, what do we know about? Oh, okay. So let's go to this. Where is D? D in our problem here is here, right? So what happens here when you increase that? So again, intuitively, as D increases, our central max increases. Yeah.
Yeah.
Central max increases as well. Okay. Now, why is that the case? Because you're making a bigger and bigger and bigger triangle. So this is wrong. Okay. Where is L? Where is I? Intensity doesn't really change width. It just makes it brighter. So this is wrong. So our only possible answer, A. And if we go back here to the formula, what happens when you increase this? This in when you increase let's okay, let's do it like this. Um, let's draw it here. Lambda is proportional to sine theta, right? And sine theta is basically the width of the central maximum. Is it?
Mhm.
Okay. Uh, so
Lambda.
yeah. So as you increase the, okay. So in this case, as you increase, okay, I have just eliminated all my answers. All right, all right. So as you increase lambda, the wavelength, then the central max also
For-
goes up, right?
If it can help,
Okay.
if it can help, I have the answer
Okay, what's the answer
because
here?
I got it wrong. The answer is D.
D. All right, let me see
I
why. Okay.
like.
All right.
Okay.
Uh okay, let's get rid of the intuitive thing then. I actually now
Mhm.
that I think about it. Okay. Oh, okay, okay. Yeah, I got it. I got it. So never mind what I just said. Let's lock this for a while.
Mhm.
Let's remove this bit. Okay. So what happens here? Just think about it this way: the narrower it is, the more interference goes. Okay. So okay, let's do it intuitively again, but like this: when W is large, right? There is little interference, and this there is little interference. So this means that there is smaller central maximum. Okay. There we go. So in other words, large W means small central mass. Okay.
Mhm.
Okay, so this is the idea here. So yeah, the correct answer is D. Remove that, and correct answer is that. Okay.
Um, sorry,
All
I
right.
forgot about interference. I forgot what it meant.
Okay. So basically, what's gonna happen here? This is a single slit. Let's do it over on the side. Okay. So if you have a single slit like this, and then you have your whatever wave it is, but most of the time you just say it's light, right? So what's gonna happen here is there's going to be kind of a light ray going from here to here, and let's say this is your screen, and then there's going to be a light ray going like that. So from the edges of the slit, there are gonna be two light rays which interfere at this point. Okay. Now, what do we
Oh,
mean by interference here? This is basically where we have superposition. Okay.
and why did they bend and not go straight?
It's just one property of waves. Okay. There's gonna be a part of the wave that kind of goes like this as well, and part of the wave that goes like that. But basically, to make it easier for us to analyze in physics, because essentially in all the other places it happens. So what we're doing is we're ignoring all the other waves that go from that edge to here. Okay, we're ignoring it for now. Our interest would be just the ones where we have some weird pattern going on, and that's exactly what's happening here. Okay, so what's gonna happen here essentially is in this region. In this region, this is gonna be bright. Okay. Okay. Have you done this experiment yet?
We did, but I completely forgot about it.
Oh, okay. All right. Usually when you do this experiment, it's with a double slit, not really a single slit. So
Yeah.
a lot of the time though, for a single slit, it's just a theoretical application. So yeah, I understand if you wouldn't remember. Yeah.
Yeah.
Okay. Yeah. So again, that light will always spread throughout wherever, but um, in the interest of making it easy to analyze, we just look at these two waves. Okay.
Mhm.
All right. Okay, so let's move on. Where is it? Okay, so this one's done. Ah, okay. This next problem. Okay, next problem here is the half-life problem. Excuse me. Okay. Okay, so this thing has a half-life of 5 hours and a decay constant lambda. At time 20 hours. N nuclei uh, present in the sample. What's the activity of the sample at t equals 5 hours? Okay, so there's an easy way to do this, but there is a formula as well. So let's do the formula first, and then we do the easy way. Yeah. Where is nuclear
Okay.
and quantum? The structure, half-life. Here we go. Okay. Okay. The since it says activity here, there is a formula for the activity, and that's equal to the activity is equal to the decay constant times the half-life. This is by definition.
Okay.
Okay. Um. Okay. So. Okay. So what we're gonna do here now is there is another version or not. There is a continuation to this. This is also equal to n0 times lambda times e raised to negative lambda t. Okay. Now, which version do you use? You could use either version to find the answer. Okay. But here's the idea. The shortcut here involves, because you have two times, right?
Yeah.
We're just gonna do a ratio. Okay, so in this case, let's just say a at 20 hours. I'm sorry, we want 5 first. A at 5 hours divided by the activity in 20 hours. That should be equal to, we'll use this, okay? So lambda n0 e raised to negative lambda. Our t here is 5, negative 5t, okay? At 5 lambda, okay? And then here on the denominator, we also have the same thing, lambda n0 e raised to negative 20 lambda here. So this cancels out. Okay.
Okay.
All right. So from here we just continue with the this. Let's just express a5 now. Um Hold on. Is there a shortcut? Yeah, I think so. We'll do that later. A20 times e raised to negative raised to negative lambda, and then that's gonna be minus, it's gonna be 5 minus 20 is 15, right?
Yeah.
Okay, so that's gonna be 15 lambda. Okay. All right. We know, and I guess that's basically it. This, and then that's the first part. But remember, we can also use that that the activity is equal to lambda times n, right? So at a20, so a20 would also be equal to lambda times n already, because you have n nuclei present, right? So that's all we have to do now. So substitute that in. So a5 would be equal to lambda n e raised to 15 lambda. That's it. Okay. But that's not in any of our choices, right? Okay.
Yeah.
So in this case, you can already see this is taking too long.
Hmm.
So
Can
let's
I ask a
go
question?
ahead.
Um, in one of the working hours, it said 20 minus 5 is 15.
Mm-hmm.
Then 15 over 5 is 3, and that means it's 3 half-lives.
Yes, that's correct. That's actually the shortcut. This is what we do. So the half life here is we're given half life is equal to 5, right? 5 hours. So that means 20 hours is equal to 4 half lives, as you mentioned. Okay, and then what's the other one? Yeah, that's it. 4 half lives, right? So that means what I'm fond of doing here, once we have an even number of half, or no, not a even, a whole number of half lives, is what I do is I just double it. So what I normally ask students to do here is they kind of set up a mini table to make it easier to do, or you can just do the math straight away. This is for those who are not so good with the math. Okay, so what I do here is time, and then whatever that x is. Okay, so this time is gonna be 0 in terms of half-life. So t1 half, t 2t half-lives, 2 half-lives, 3 half-lives, and then we get to that idea of 4 half-lives here, right? Okay, now here at the here at the end, what is our activity? What is our x? Activity n, right? There are n. So n. So every time you go that way, you just multiply by 2, 2n. And this is our interest, 1 half life, right? So this is
Yeah.
gonna be 4n, and finally this is gonna be 8n. If you want to continue, we started off with 16n. Okay. All right. So now that we know what the n is, we can now calculate um, the activity. The activity, again, just go back to that formula. Activity is equal to number of particles, 8n, times the decay constant. And therefore, answer is B. Okay?
Huh. Okay.
All right. But okay, just a quick question. That sigh, that last sigh over there, what was that about? I'm just curious.
The sigh?
Yeah. Yeah, when you said that.
Oh,
I'm just curious.
maybe it
Don't
was.
worry about it.
There's voices outside. I don't think it was me.
Oh, okay. All
There's
right.
my family is outside.
I see. All right, I got that. Copy. All right, let's this okay. Oh no, not this one because this is a part B.
I attached the whole task, but the actual question is very small.
Yeah.
So there's a big part that's just content.
All right, let's do the multiple choice first. Copy this one. Okay. Okay, I got that. All right. Here we go. Simple harmonic motion problem. Okay, so when you have an object here that's performing simple harmonic motion, and when the displacement is half the amplitude, that's what it means, right? Half the amplitude, the
Yeah.
kinetic energy is E. So, what's the total energy of motion? So remember that if we go back to the data booklet again, okay, simple harmonic motion would be, here we go. Energy. Okay, so the total energy, let's just write the two equations again. The total energy here is 1/2 m omega squared x0 squared. Okay.
Yeah.
Okay, and then the kinetic energy would be equal to 1/2 m omega squared just x, right? So in this case, our x is gonna be equal to x0 over 2. Oops, I forgot the square there. Okay, so from here, if we substitute that in there, that's gonna be 1/2 m omega squared x0 over 2 squared, and that's gonna give us 1/2 m omega squared x0 squared then over 4, right? Which if we rewrite further, this will be 1/4 of ET. Okay, so what's our
Okay.
answer? So E equals EK, and that's that, right? So in this case, E is 1/4 ET, the total energy. So total energy here is equal to 4E. Answer's D. Go
But
ahead.
do we not use potential energy?
We could, but in this case, oh, sorry, this should be potential. You're right. This should be potential, right? Okay.
Okay.
Right. Okay, so let's remove that. That's potential energy, but it's still gonna be labeled E, right? So,
Yeah.
sorry, that's not E. That's just potential energy. So, this is the potential energy, right? So what's the kinetic energy? So the kinetic energy would be what's left over, 3/4, right? E. All right. So let's change our final answer. It's not 4E. The final answer is total energy. Okay. Um, kinetic energy is what? Okay. So from here, the EK is 3/4 of the energy, and this is also equal to. I think that's it. Total energy is therefore 4/3 E. Okay.
I think that's correct.
Okay. Hold on.
For this,
Something's
yeah.
wrong with my brain right now. Let me double check that. Okay. Total energy is that. Potential energy is that. Okay. And therefore the potential energy is 1/4 of the total energy. Okay, this should be total energy. That's what's missing. Okay. So let's finish it up. Okay. So now that we've figured out what the kinetic energy, what the total energy is, and this, as mentioned, is E. There we go. So there, this is more complete. Okay, so from here, total energy is still the same, 3/4 E. So the total energy would be equal to 4/3 E. Okay.
Okay.
All right. That
Yeah.
is more convincing, I think. I also am more convinced with that. All right.
Mhm.
Let's move that up. Let's skip that for now. This is okay. This next problem here is about what's this? The energy levels in a gas atom. Okay. So before we solve this problem, let's recap again. Okay, let's make this a bit bigger. Let's recap the formula again. That for quantum mechanics, the energy of a photon is equal to h lambda, or you can say that's equal to hf, yeah, hc over lambda here. Okay.
Mhm.
Hmm. Okay, let's lock that so I can erase this a bit. Okay, so going back to this then, so what does this particular equation mean here? So remember, this is increasing energy. So, okay, let's take a look at these three, transitioning from E2 to E1 first. So E2 to E1, this would release photon, right? Photon, small energy photon. Let's just write it like that. Okay.
Mhm.
So E1, E2 to E1 is a small energy photon, low E photon. Okay. E2 to E0 would be high energy photon, right?
Yeah.
Okay. Now, let's take a look here. For low energy photon, if the energy is low, then that means the wave, this means this is high wavelength, right? Similarly, this high energy photon would mean a low wavelength and a high frequency. Okay. So low
Yeah.
frequency in this case. So let's take a look at the two statements 1 and 2. So which one is correct according to our excuse me, to our analysis here? So one is wrong, right? E2 to E0, high frequency, correct, right? Now, last thing we can do is how many lines will appear. We have that and we have that, and we still have a third. We have this E2 to E1 to E0. This is also possible. So there are three photons possible to produce three photons. Okay, possible to have three photons. So this is correct. So our final answer is 2 and 3. So from our choices, that's going to be C.
Sorry, can I ask a question?
Go ahead.
But if um if lambda is indirectly proportional to f, and we said that the E2 to E1 is the shortest
Yeah, it's a short.
energy is proportional to f.
Yeah.
Why is it?
Okay. So remember, the way I always think about it, just to kind of help remember. Okay. Now, high frequencies. Think about it this way: if you are actually making something vibrate at a low frequency, you yourself are doing that. So let me uh let me stop sharing for now.
Mhm.
Okay. And let's get here. All right. So if here I have a ruler and I'm gonna make it vibrate, you can do this yourself, right? Right now with your pen. Now compare this to doing this.
Yeah,
Which one are you exerting more energy in?
in the high
High
frequency.
frequency. So always think like that. The higher the energy, the higher the frequency.
But shouldn't the wavelength then be the shortest because wavelength is indirectly proportional to frequency?
Yes, that's right. So short wavelength, right? So
So one is
actual
correct.
hold on. Actually, no. The other way around. When the frequency, because let's do it in terms of the formula first. Okay, let's go back to the
Mhm.
board. And let me share the board with you as well. Share that again. So remember, what's the speed of a wave will always be equal to the frequency times. You know what? I won't use v here. I'll use c. Okay. So
Mhm.
the speed of light will equal the frequency times the wavelength. So what happens here? In a vacuum, this is constant, right? So this means
Yeah.
if f increases, the wavelength decreases. Okay. So in other words, the
Yeah.
more frequent you do the vibration, the smaller the wavelength will be. Okay.
Yeah.
Now, um, so from there, so if we go back here, low energy, low frequency, high wavelength. Okay. Large energy, large frequency, low wavelength. That's how you kind of remember that.
So energy is low, frequency is high.
Yes. No, energy and frequency should be the same. Low energy, low frequency. It would be
Okay.
the wavelength that would change. Okay, it would be go the other way.
Okay.
Mm. All right. So, okay, is everything clear there?
Yes.
All right. So let's move on. What's the next problem here? Not that. Not that. This one's done. Let's take a look at this later. Oh, okay. I think I see one. Then that's A. This is B. This is C. Okay. All right. This is all one big problem now, right? Um, can we get to all of these later? I think so. Okay. All right. So let's take a look first at the setup. So you have an experiment wherein what are you doing? The length and the distance it goes down are being investigated, right? This is actually a really good IA if you think about it.
Yeah.
Okay. Um. Okay. Go to mean value. Okay. All right. So that's the first image. Let's take a look at A. Where is A? Uh,
Is discuss the
discuss the
values
values, right?
that the
Mhm.
yeah.
So let's just put this here. Discuss the values. Okay. In this case, you are actually supposed to kind of comment on whether which one is accurate, which one is precise.
Oh.
Okay. Well, that's the way I
Okay.
see it because there's no other way that I can think about. Um, unless I have the marking scheme here, which I don't. That's the only thing I can really think of. That's actually being asked here. Which one is accurate? Which one is precise? Which one is correctly done? To the correct number of sig figs, like that. Okay. So in order for us to actually do this, we need to find the average, right?
Yeah.
So,
I
so
found that A was correct.
okay. So this is correct. So let's just note that there. This is correct. Correct mean, right? Let's zoom in a bit so it's easier to see. Okay, let's read. Oops. Okay, so correct mean. There we go. Let's lock that. Let's redo that briefly. Okay, again, the first one is correct mean. Okay, what else can you comment on?
That it's accurate.
I wouldn't really say accurate at this point. Okay, I'm gonna say something like this. This is incorrect sig figs. Incorrect number of sig figs. Okay.
But how come if they only have one?
Mm-hmm. Now, so before we get there, so basically you can comment on this as incorrect mean, right?
Yeah.
But correct sig figs. Correct number of sig figs. Now, the reason for that is, remember, for significant figures, okay. Now, when you're taking whenever you're, what's the rule? Okay, the rule is if addition or subtraction, okay, follow a number of decimal places. Yeah.
Yeah.
Okay. Um. Okay, so we can actually note it here again. Which one has the correct number of decimal places? A A has correct number of. Okay. Let's just note it here. Correct number of decimal places. Okay.
Mm,
Now, if you
I
have,
understand.
okay, if multiplication or division or other, what's this? Other operations, okay, follow number of sig figs. Okay, specifically here for addition, follow the least number. Same thing here, follow the least number of sig figs. In this case, they all have two sig figs and one decimal place. So the correct answer would be 2.9, right?
Yeah.
Okay, where is B? Okay, I see a graph, but I do not see a question for B.
Oh, B I didn't need help with. It was
Ah,
C and
so we'll skip
then
B.
D and D.
We'll skip B, yeah?
Yeah.
Let's go to C then, copy that. Okay, here we go. So theory predicts that this is the relationship between those things, okay? So calculate
That's
X
the graph.
and Y. Okay, calculate means we need to get a value, okay?
Yeah.
So,
From the graph, there's the
so I
graph
think we
is
need a graph.
for this.
Okay.
Yeah.
Okay, can you just tell me of what, okay, never mind. I'll put the graph up. Okay, so
Okay.
let's put the graph here. So theory predicts that that's the equation where E and I are constants. Fundamental units of I are those and those. Okay, so all right. The trick here, whenever you see a graph and then you have a theoretical basis like this, okay. The trick is to use the equation of the slope. Okay. So
Okay.
so use the equation of slope. Use slope equation. Okay. So in our case, our slope, we can just write it here. We're not even going to do it more very mathematically. We're just gonna write that slope is equal to d, change in d over change in w, right?
Yeah.
Okay. Now, um, since this is a straight line, we can just say that's, and then it's basically zero. Okay, what else can we do? Okay, the slope, we can now compare this to the actual equation. So we can say here, before we continue, we can say here that d is equal to, we'll change that into an equation, equal to some number, let's just use m, okay? D is equal to m, then w raised to x, l raised to y, all over ei, right? Actually, I'm not going to use
Yeah.
m, I'm going to use k. Let's lock this, all right? So this is k. So what now we're going to find, um, what are we going to do? So here, um, we will put everything together that isn't W or isn't D. Okay, so we're gonna write it now as D is equal to um I'm putting W raised to X here. Okay, and I'm putting everything together, K um L raised to Y over E I. Okay, now
Yeah.
all right. Actually, yeah, we don't need this slope equation anymore. Now, what we can do here is we can compare this to the slope equation. Compare, right? So, because our y is d and our x is equal to w, right? Is it just w there? It's just w, right? So that means the slope is equal to k l raised to y over e I. Okay? So in other words, we can now say that x equals 1. Because that's the only way that w raised to x equals w, right?
Mm-hmm.
Okay, so that's the first part. Yeah. Okay, the second part is determining L, right? Um, think about it this way though. What's the unit of the slope? Let's put the units in now. The d, this is equal to basically d over w again, right? So let's put the units in.
Yeah.
D is in centimeters, correct? So let's put that in. W is in newtons. Let's put the unit in for everything else. We don't know the unit for K, right? L
Yeah.
is a length, right? So that's gonna be meter raised to Y. What's the unit of E again? Let's take a look at the given info. E and I, what are the units? Meter 4 and kilogram meter per second squared. So this is meter raised to 4. But cm is basically meter, so we can get rid of that, right?
Yeah.
Okay, meter, that's E, and then what's I again? I is, sorry, I is m raised to 4, E is kilogram per meter per second squared. Kilogram per meter per second squared. Okay, and then we can change Newton into kilogram meter per second squared, right?
Yeah.
Okay, let's start canceling stuff out. This kilogram here cancels out. This meter and this meter cancels out. We are left with s squared. This is s squared, cancel out. Now k, mm, the slope itself usually doesn't okay, never mind. What are we looking for again? Let me double check. We are looking for the value of y, right? So
Yeah.
we're left with, on this side, no unit anymore. I'm just gonna write it as no unit. Okay, that's gonna be equal to k meter raised to y over meter cubed. This 4 and this minus 1 kind of cancel out. We're left with 3, right?
Yeah.
So if the whole thing has no unit, then that means k also, we can ignore k because k is normally just a number, right? No unit.
Mm-hmm.
Okay, so no unit gives you no unit, so that means y equals what? So what do we get here? Y equals 3, because that's the only way that meter raised to y and meter cube cancel out and giving you no unit.
Huh.
Okay,
Okay.
all right. Okay, so that's what, whenever you see something like this, that's immediately what you do. You convert this into an equation, and the equation is, once you have the equation, you basically change it into a form that looks like y equals mx plus c. Okay,
Okay.
all right. Okay, so that's it. We have one more problem. I think we'll just finish this last problem. Okay, so in this case, okay, copy this. Okay, last question here. Okay, so while this is loading, um, okay, never mind. We need to suggest an appropriate unit and a percentage uncertainty for A, right? Okay.
Yeah.
What instrument do we need for determining B? Look, it's in millimeters. And we go to three to two decimal places. So we can't use a ruler here, right? Um,
So what do you?
we will use here. Okay, here's the thing though. This really feels like I will tell you this much. This doesn't feel like an A level or rather an IB question. This feels like an A level question for me.
Mm.
Just so
It
you
was
know.
in our exam.
Yeah, but it's gonna be
Yeah.
still useful either way. Yeah. So the idea here is for lengths, there are usually three instruments we use for small lengths. We have a ruler, we have a micrometer, and we have a vernier caliper. Okay. Now, for a ruler, this is at you can do up to 0.1 cm or 1 millimeter, like that. Yeah. A vernier caliper is
Yeah.
accurate up to 0.01 cm or 0.1 millimeter. Okay. A micrometer is gonna be accurate to 0.001 cm or 0.001 millimeter. So we can see here already which instrument is the best.
Micrometer.
The micrometer. Okay. So this would be that. Okay. Now, how do you calculate the percentage uncertainty in A? Let's do that last one. Area, as mentioned in the formula here, is just A times B, right? So
Yeah.
percentage uncertainty in A, let's just do it like this first. In A, that should be equal to the percentage uncertainty in small a over A plus the percentage uncertainty in B. Like that. Then all you have to do, you don't even need to calculate the area anymore. You're just gonna do that, delta A over A. Okay. What's our small a? That's gonna be 1 over 28 plus 0.05 over 3. Just put those numbers together, and that's your answer.
Okay.
Okay.
Thank you.
All right. Okay.
Yeah.
I remember before we go, you did send me a message last time when I scheduled for
Yeah.
rescheduled it for Monday. Let me.
Would you be available or would it be too late?
I could move it to after 3:40. That's gonna be 6 hour difference. Yeah, I think I'll be fine. I'll move it. Okay.
You can let me know last minute if you feel like doing it that late, but I
Mm-hmm.
think it'll be safer because I'm most likely to stay in school.
All right. Okay. I think we're okay here though. So
Okay.
excuse me. So yeah. Stop sharing. Yeah, I think we're okay for Monday. I'll just move it to. Yeah, I'll just move it to around 3:30. It's fine. Yeah.
Okay. Thank you
Okay.
so
All
much.
right. So I'll see you next Monday then. All
Yeah. I
right.
wish you a fast recovery.
You too. You too. All right. So I'll
Okay.
see you then. And
Bye.
okay. Bye bye. Have a good day.
Thank you. You too.
All right. That's the end of that lesson. Yes, I am sick, and so is she. Um. Anyway, I mentioned this earlier. Whatever that virus, that new virus that's going around, I think it's just getting a lot of media attention. But here's the thing. I remember just one time. Uh, there was this. When did this happen? Right when, I don't want to. I can say it. It's I don't really mind getting demonetized because I'm not making money yet. Anyway, right before COVID start, when COVID just started, and it wasn't really the pandemic. It was yet. It was just being monitored by all the countries. I remember seeing numbers, and the numbers that at the time I didn't pay much heed to it, but it did ring some alarm bells with me then. There were the two numbers that were really bad in combination with each other at that time were the amount of infections and the amount of, well, basically how fast it was spreading at that time, and also the amount of people dying from it. So especially when it was compared to SARS and Middle East Respiratory Syndrome, MERS. Uh, okay. Now, having said that, looking at the numbers for this news, not even new, this news virus that I said, it's being covered in the news a lot. It's not as bad, not even as bad as the other would-be pandemics by that time. Okay, and then another thing that I discovered. Well, if I'm wrong, then I'm wrong, but let me know if I am. Yeah, but another thing I discovered was this virus that's going around. It's not really new. It's if I recall right from what I read, it was officially described early 2000s, but it's been around for at least since the 1970s, maybe even earlier. So in other words, yes, there is a virus going around, but A, it's not that dangerous. It's mostly really like a cold. And B, it's been around for a while. And oh, and one last thing that was mentioned in the news articles I mentioned is that it doesn't mutate quite as fast as any of those viruses that were shown before. So in other words, yeah, we'll get sick and everything, but A, it's gonna be mild, and B, it's gonna spread, but it's not gonna be that dangerous, so to speak. Okay. So anyway, I'm getting off track. So yeah, so that's the end of the lesson. Hopefully those who well, you can learn something from that. So we'll end the lesson here today. And as always, before you go, don't forget to like, share, and subscribe to the channel on Facebook, YouTube, TikTok, Instagram, and Twitch when we go live. So with that, I bid you all a good morning, good day, good afternoon, good evening, good night, wherever you are in the world, and stay freaky, everybody. Bye bye now.